Hi everyone, welcome to my channel. So in my previous video, we talked about agglomerative clustering, and in that video, we just took the distance matrix and input to agglomerative clustering as given. But in this video, we're going to talk about how we get that distance matrix. More specifically, we're going to talk about DDTW, an algorithm to measure the distance between two time series. Okay, let's study together. So what is distance? If we're talking about the distance between two objects on a table, then we can measure it quite easily by using a ruler, perhaps. But we're talking about distance between time series. What does distance between sequences represent? It basically represents dissimilarity or similarity. Similarity and dissimilarity are opposites. So if two time series are exactly the same, then they will have zero dissimilarity, but the similarity between them would be 1. Let's say that we have a scale ranging from 0 to 1, 1 being perfectly or exactly the same, and 0 being totally the opposite. The term dissimilarity might be used more often, but we can see the term similarity used in many literatures as well. And even though personally I'm more used to the term dissimilarity, I'm going to use this term throughout the video. Now, the most common way to compute distance between two time series is using the Euclidean. So let's say that we have the upper series and the lower series. We must match by the index. We must match the time series based on the index and take the square difference from every index. So here we take the square difference from the first index of both series. Yeah, and we just do that for every single index, the second one, the third, the fourth, and so on. And then we sum them up. So it will be the sum of the square difference. Okay, for all index. And then we take the square root of it. Another common distance method is Manhattan distance. With Manhattan distance, we don't take the square, and we don't have the square root as well. Okay, so that's very straightforward. But the main disadvantage of using Euclidean or Manhattan distance, or just in general p-norm distance, is that these methods require equal length in all time series, but it's very common to have a dataset with unequal length of series, right? So there are many alternatives developed, and one of them is derivative dynamic time warping. And this is our focus for this video. However, to understand this, I need to cross this word first, and we need to start from understanding dynamic time warping first. Okay, so I'm going to try to explain this very briefly. So basically, dynamic time warping is a way to align the time series so that the distance between them is minimized. Let's see, we have the upper series, which is black, and the lower series, which is blue. And both series have a subsequence which is bounded by the pink tape that are exactly the same. So if we can align them in such a way so that the distance between these subsequences is 0, then I think we can minimize the distance between them. So rather than aligning by the index like this, we can align it like this. Okay, so it's like shifting the series so that these subsequences could opposite each other, and then for the rest of the subsequence that haven't been matched, they can find a way to find a match, to find an alignment. For example, like this. This is okay, and we will see why this is okay in a moment. We want to do this automatically, right? So we need an algorithm to do that. And using DTW, we have 3 steps. Okay, so the first step is to build a local cost matrix, LCM. The dimension of this matrix would be the length of both series. So in this case, I already made a simple matrix here. The rows, the total rows is 8, and the total columns is 6. So we can say that the length of the first series is 8 and the length of the second series is 6. And then for each element, for each cell of this matrix, we calculate the pointwise distance. Okay, so let's say that here in this box, red box here, this is the distance between the 8th element of the first series and the 6th element of the second series. Alright, once we have filled all those cells in the LCM or local cost matrix, we can move on to the next step. The next step is to find the path that could minimize the cost or the distance. Okay, so here's how it goes. We always start here, the bottom left here. From this point, we have 3 options. We have 3 paths. To the right, one cell, to the top, one step up, or one step diagonal, like this. And then among these 3 values, we choose the minimum and go towards that direction. So let's say that the minimum among these 3 values is this one. So from 0.0, we go to 1.1. And then we make the path like this. Okay. And so even though these look like coordinates, but it's also telling us about the index of the series that could be matched. And then if we keep going up, if we keep going, like maybe the path looks like this. The algorithm could return the path too. Visually, the path looks like this, the red line here, but if we do it with program, then we would get a list of coordinates. It's more precisely to call this as the warping path. So yeah, the warping path would look like this, like 0, 0, and then 1, 1, and so on. So if we go here, the next, that would be 1, 2. Okay, so I index it starting from 0. Okay, so this is 0, and then this is 5. And then this is 0, and this is 7. And so on. To understand this, 0, 0, or 1, 2 here, 1, 2 here is just like reading the coordinates. So the first number is referring to the index of the first series, while the second number is for the second series. Okay, every time we land on a new cell, we would only have these 3 options: to the right, to the top, and diagonal like this. Okay, this is what it's called step pattern, by the way. We have this because we have several constraints. So yeah, I'm going to discuss 3 of them. Like, these are the most basic ones. The first one is the boundary condition. So the boundary condition means that the first element of both series needs to match each other, and the last element of both series also needs to match each other. Okay, so no matter how we align this in the middle of the series, the first, like the very beginning and the very end of it needs to match each other. And the second one is continuity, or some people call it symmetric continuity constraint. So we have a warping path that looks like this earlier, like right, 1, 1, and then 1, 2, like this. Let's say that we have A, B, And then the next warping path is A star, B star. By the continuity and symmetric continuity or symmetric continuity constraints, A star minus A has to be less than or equal than 1. And so we have two requirements that needs to be true. Okay, and B star minus B has to be less than or equal to 1. This alignment here on the top is okay because, well, 1 minus 1, so the first, if we take the difference between the first indices 1 and 1, it's less than or equal to 1, right? And then between 2 and 1, that is exactly 1. So this warping path is okay. Visually, 1, 1 and 1, 2 would look something like this. The first index from the top series would have been aligned twice. Okay, let's go to the third constraint. The last one is monotonicity. Visually, we cannot have something like this. So the alignment lines cannot cross each other. Okay, they can only have the same tail or like the same head, or perhaps like this. This is okay. Or something like this. Okay, this is okay, this is okay, this is also okay, but this one is not okay. So those are the three basic local constraints. In some literature, they are called the local constraints. And here, Sakuchiba and Itakura are the global constraints. We're not going to use this actually, but I still need to mention it very briefly because in the documentation, if you look at the documentation of the function that we use in the coding section, you will see these arguments. So basically, Sakuchiba and Itakura are additional constraints. Sakuchiba deals with masking some region that cannot be traversed when we are looking at the path in the LCM. The Itakura works the same actually. So remember that we have a step pattern that looks like this, right? At each point, we can go right, go to the right, go to the top, or go to the diagonal. This diagonal here must have a slope, right? And Itakura can let us modify the slope. So perhaps the slope would be big like this. When we go to the right and we go to the top. So the step pattern could be modified a little bit. Okay, but we're not going to use this anyway, okay? So don't worry if you don't understand this. Okay, so once we found the path, our path looks like this earlier, if I remembered correctly. Okay, so this is our path from the previous. The next step, which is the final step, is just to compute the cost or like the numbers in the cells that is traversed. I have to tell you some details about the step pattern. There is another detail about it, and that is each path has its own weight. But since the default of DTW, well, I mean, not the default, I mean, perhaps the most used step pattern has weights 1 in each path. So this problem is simplified to just adding the distance, point-wise distance that is traversed by the path. After adding the distances, we just take the square root and that's the distance. That's it. We have the distance between two time series. Okay, so that was DTW. Now we're ready to talk about derivative DTW. Okay, this method was developed by Kyo and Bazzani in 2001. So this is, I mean, the name is quite straightforward actually. We take the first derivative first of each sequence and then compute the distance of the new sequences using DTW. Okay, so there's an additional first step. Let's say that we have three sequences here, and then we take its derivative. That will give us three new sequences, and we use this to compute DTW. And the formula for calculating the distance, the derivative of the sequence is defined here. Let's look at the top sequence here, okay? Let's say that we want to calculate the derivative at that point. That point would be the qi, okay? And then qi minus 1 would be the previous value, and qi plus 1 would be the next value. Okay, so for every point in the sequence, we need the previous and the next value to calculate the derivative. That's why if we have length n for the raw sequence, the derivative sequence would have length of n minus 2. Alright, so far we are talking about distances between two time series. But now let's say that we have a data set, a very small data set of time series, perhaps of 5 time series only. Then how can we calculate the distances? It's just a little extension actually. So we would create a distance matrix like this, 5 by 5, since we have 5 time series in our dataset. And then let's say that this is for, the rows are for time series A, B, C, D, E, and the columns are also labeled the same way. Let's say that we want to fill this out. This would be the DDTW between time series A and B. And so, for example, like this would be the DDTW between time series A and E. Maybe you might have guessed that the distance matrix would be a square matrix. Okay, and its diagonal would be 0, since the distance between A and A must be 0, right? The dissimilarity is 0 because it's exactly the same. It's not different whatsoever. So that's why its diagonal must be 0. And finally, the distance matrix, any distance matrix is symmetric because the distance between B and A must be equal to the distance between A and B. Okay, so that's it for the theory section. Before we go into the coding section, I just want to give you some references. So what we just discussed is just scratching the surface. If you want to know more about DTW or DDTW, please refer to these articles. So now we're moving on to the coding section, and in this section, we're going to apply DDTW to measure the distance between two time series and eventually between time series in the dataset. To measure the distance between time series, we're going to use tslearn library. There are many other libraries in Python that could do the same job, but in this video, I'm going to use tslearn. And from tslearn, we have the module metrics, and from there we import two functions actually, DTW path and cdist DTW. To apply DTW, the first thing we need to do is to compute the derivative of each sequence, right? And this function will do the job. So this function is just the translation of the equation we saw earlier in the theory section. More specifically, this line is the exact translation. Now I'm going to show you the plot of the raw CPI series and their derivatives. Okay, so actually this part is just about the data cleaning and stuff like that. Anyway, this is the raw series. And as you can see from the values on the y-axis, the range is huge. Like in the first row here, the range of CPI starts from around 10 to around 20. But at the bottom row, the range is already around 220 to 300. Oh, by the way, the precedents or like the series are sorted this way from left to right, top to bottom. So Woodrow Wilson was the first president in this dataset, and then Warren G. Harding, and then Calvin Coolidge, and so on. And this is the derivatives. Okay, so perhaps it's a better idea to compare it side by side. The left column plots are for the raw CPI series, while the plots on the right column are the derivatives. Okay, and notice that now that we're taking the derivatives, the values of the series have much smaller range. Like for example, the top plot here, it ranges from 20 to 25. Well, actually a little bit less than 20 to around 25. But after taking the derivative, the range is only from 0.0 to 0.5. This is another reason that I want to apply DDTW for this use case, because the range for the raw series is too big. Okay, so yeah, these plots, these codes are for the plots. Okay, now that we have the derivative sequences, we can move on to the next step, which is the DTW part. Let's now first calculate the distance between two time series only, okay? Later we will move on to calculate the distance for all pairs of time series and make it into a distance matrix. I actually already make the object to prepare the dataset for calculating the distance matrix, because this is the requirement from TS-Learn. Yeah, maybe I should explain this first, since this line is written first. So to compute the distance matrix, TS-Learn requires a list of lists as an input. That's why we make it like this. Okay, and we store it as clean series. Okay, anyway, now let's say that we want to compute the distance between CPI during Trump presidency and during Biden's presidency. So to be exact, Trump's presidency was around from 2016 to 2020, while Biden's series start from 2020 to the last date of this, the last date in this dataset, which is January 2024. Okay, we save it as Trump and then Biden. Now this is the important line here. To calculate the distance between two time series only, we use DTW path. And for the arguments, there are several other arguments, but I just leave them to the default value because we're doing the basic DTW. Some of the arguments are about Sakuchiba and Itakura, but the default value is none anyway. So if we set them to none, that means we're not setting any global constraints. Okay, so we are just left with two compulsory arguments, which are the two time series that we want to compute the distance. After we call this function, we will get two things. The first one is the distance, so it will be a number. And the second one is the warping path. The warping path would be represented by a list of tuples. And then for the next section here, I am using the path Trump Biden. Oh, sorry. I'm using path Trump Biden to make the alignment plot. And then, yeah, I also write the distance in the plot. Actually, if you don't want to know the warping path, you just want to get the number, we can just call the function DTW. But if we are calling DTW underscore path, we will get these two things. So here is the alignment between two time series. We can see that even though the length of the series are not the same, but we can still align it and find the distance. Okay, so the distance between the upper series and the lower series is 5.96. The upper series belongs to the CPI during Donald Trump's presidency, while the bottom one belongs to the CPI series during Joe Biden's presidency so far. Now, if we take a closer look at it, we can see that it meets all the local constraints. For example, like the boundary condition, see the first indexes of both series are matched. And the same goes for the last one. So here's the last data, and it's matched with the last. Is it clear enough? Because there are two lines overlapping here. Oh yeah. So I guess the last two elements from the Joe Biden's presidency are aligned with the same point. We can verify it in the warping path. Oh, actually no. So this is the warping path. If this is the alignment, we can see the warping path here. So we're just using each coordinate or each tuple to draw this. And at this point, this particular point, it would be at the coordinate of the length of Trump's CPI and Biden's CPI. Okay, now let's take a look at it. This horizontal line, well, if we take a look at the coordinates, they must have the same y value, right? They would have the same second value, which is 5. But the x values keep changing. So we can imagine like this point would have the warping path 10, 5, and this one have the coordinate 20, 5. We can see that the fifth value of the CPI during Biden presidency is matched with many points from the early, at least the early subsequence of the Trump CPI. And this is the representation. So this is where the alignment lines are gathered in one point. And this is okay. It still meets the continuity constraints. For the monotonicity constraint, it might be less clear if we see it from here, because the alignment lines seem to overlap with each other. But we can see from here, we can verify it. Because if it doesn't meet the monotonicity constraint, I don't think the warping path can go on like this. I guess it will go, after going up or just going horizontal, they would go back. And that doesn't make sense, right? They would go back like this and then before going up again. So, yeah, we don't see that here. We won't see that here, actually. Okay, it is guaranteed that we will always meet the requirements. Okay, so that is the distance for between two time series. Now let's move on to calculate the distance for all pairs of time series. And we can just use cdist underscore DTW. Actually, the arguments of this function is exactly the same as in the function of DTW path. Yeah, it's just we can input a list of lists for this function. That's the only difference. In other words, we can put a data set into cdist DTW. And again, because we're not imposing any global constraints, we can just leave the other arguments, including Sakuchiba and Itakura, as none. Okay, now let's see the distance matrix. The colors are not really important actually, but because I'm using heat maps from Seaborn, that's why it has colors like this. But perhaps if we want to connect this to the clustering video or the clustering result, I guess we can see quite clearly why the clusters results are like that. Okay, so for this cell on the bottom left, it is the distance between Joe Biden and Woodrow Wilson. It's quite high, relatively high, which is 8.9. These are the numbers. Maybe it's better to zoom out like this and just interpret this based on the color. So the brighter the color, the farther they are. And we can see that the rows for George W. Bush here and the rows of Joe Biden are very bright. And then this row, this is for Jimmy Carter. Let me zoom in. So this part here, Jimmy Carter, Ronald Reagan, George H.W. Bush, and Bill Clinton, and perhaps Donald Trump. They roughly have the same shade of colors. And the darkest of all is this one, between John F. Kennedy and Lyndon, and perhaps Dwight D. Eisenhower as well. I guess it makes sense now. Well, looking back from the clusters results, it'll make sense why John F. Kennedy and Lyndon B. Johnson are always clustered first, no matter what linkage we're using. Don't worry if you don't understand what I just said. I'm referring to the previous video, but again, this video just focused on generating the distance matrix. And yeah, you can verify, you can see that this distance matrix is definitely symmetric and its diagonal is 0. This distance matrix can be used not only for clustering. Of course, in this use case, talking about clustering, I mean clustering as the final goal, but DDTW can be used for classification as well. Okay, so that's it for today's video. I'll put the code in my GitHub. Thank you so much for watching. Please subscribe to my channel, Timely Time Series. I'll see you next time. Bye bye.